Okay, hello and welcome to the Chapter 7 Part 2 webinar. So we're going to continue on where we had left off yesterday. And so let's go ahead and do that. So we had introduced some gas laws and such. And so I think we had addressed Boyle's law and we addressed Charles' law. And there was relationships between pressure and volume, or for instance, volume and temperature, or pressure and temperature. So what I just want to do is I just want to start with some examples of what we had done. Yeah, using those gas laws, we're going to use examples 720 and 721 that are in your book. And so here's problem 720. It's on page 279 of your book. And what the question is asking is about whether the bag that is going to be used in an emergency resuscitation, and this is also known as an AMBU bag, that's like the trade name for it, but this is really just a positive pressure kind of chamber. And in the picture here, you see the gloved right hand that is over the bag, and it's a manual resuscitation practice where the bag is actually, or the bottle, it kind of looks like a bottle, but it is referred to as bag, is compressed with your hand, and that forces positive pressure that had been built up in that chamber just from the atmospheric air, or if there happened to be, for instance, I don't know, like if there was an O2 cylinder on hand and an oxygen-rich environment would have been necessary. Anyway, that air would have been introduced into that chamber, and then by squeezing that chamber, the air then flows through and out that mouthpiece mask type of structure that's on the bottom right of that image. And so this is usually given in replacement of mouth-to-mouth resuscitation. So this is just one of the common, maybe it's a cleaner process of doing it, but it can definitely provide even nice, steady and nice positive constant flow, being able to introduce that into the lungs. So anyway, this is where they're getting that question from. They say, what happens to the pressure inside the bag when the AMBU bag is squeezed? No surprise here, if you squeeze it, the air from that chamber will be introduced into the mask area, which will then be introduced to the patient. A more interesting question here, where we're actually going to apply some gas laws, would be problem 721. And this is also on page 279, and it reads, a 25 milliliter bubble is released from a diver's air tank at pressure of 4 atmosphere and a temperature of 11 degrees Celsius. What is the volume of the bubble when it reaches the ocean surface, where the surface pressure is 1 atmosphere and the temperature is about 18 degrees Celsius? So you're obviously not at normal atmospheric conditions if you are experiencing a 4 atmospheric pressure increase, and considering that surface pressure would be 1 atm, you're 4 times that. So you are not at surface, you are below surface. So the diver is obviously in water, underneath the water, at a depth that would give a pressure of about 4 atm. So, or that's from the actual tank. And so yes, these tanks are pressurized, and they need to be in order to be able to withstand the differences in pressure whenever the diver goes, obviously at a certain depth. So anyway, how would you approach this? Well, you already have a starting volume, you already have a starting pressure and starting temperature. So you already have your P, your V, and your T all at the initial conditions. The thing that you don't have is the volume at final conditions, which would be whenever the bubble reaches the ocean surface. And so if the surface pressure is 1 atm and the temperature is 18 degrees, and you have your pressure and your temperature. So what you need to do is use the combined gas law. And here I wrote it down for you in this presentation here. It's P times V times T, no surprise here. And again, all of this derives from the fact that PV equals nRT, and that R is a gas constant, and it's then ideal for gases, but it can also be used for other instances as well. So for instance, liquids, maybe some solids, but it really starts to break down and you got to add in a couple of different fudge factors. But again, you don't need to worry about that. You just need to be able to know how to apply that in this kind of situation with respect to air. And so you have to remember that you have to get the temperature not in Celsius, but get it into Kelvin. So you add the 273 if you want to be very pedantic about it, 273.15. So there's 2 additional sig figs that are typically added in whenever these kind of conversions are done. So you can look at 11 degrees C plus the 273 gives you 283 Kelvin, and the final temperature at the ocean surface, not at depth, is going to be 291 Kelvin. So in doing these kinds of calculations, you can get to a final volume of 102 milliliters. So you can see that the volume clearly increased almost a factor of 4 times. And one of the reasons for that is because there was a 4 times difference in pressure at depth versus at the surface. Whenever I'm talking about at depth, I'm talking about the pressure on the diver and that which is experiencing on the tank and stuff. You know, whenever the diver breathes out, a bubble from the regulator is produced, and if they're doing that, they're breathing from that cylinder at a pressure equivalent of 4 atmospheres below normal sea level, where it's at 1 atm. Obviously, that bubble is going to rise to the surface, and it's going to get then bigger as it does so. So this is a great example of using the combined gas law and trying to make those conversions in the temperature and arriving at the proper answer. Okay, so here's another example, 722, and this is also on page 279. And here we're going to look at a 100 milliliter bubble of hot gas at 225 Celsius and at 1.8 atmosphere escapes from an active volcano. What is the new volume of the bubble outside the volcano where the temperature is negative 25 degrees Celsius and the pressure is 0.8 atm? So yeah, so up high in the atmosphere, the temperature is obviously cooler than what it is at the ground surface, and also the pressure is slightly reduced. And we already knew this a bit from yesterday's conversation where we talked about that. As you get closer to the center of the Earth, the pressure increases as you go to the atmosphere, and then obviously into the stratosphere and into the outer space, where the satellites like to roam. The pressure is significantly reduced, right? And it's also very cold. So I believe the temperature of outer space gets close to about 4 Kelvin, so exceptionally cold in the outer, in the outer space. So with a volcano, obviously, the volcanoes tend to be, in this particular case, sitting up a little bit higher in elevation, and it spews a 100 mil bubble of hot gases, obviously at a higher temperature. I mean, normal temperature is about 20 degrees Celsius. You can see that there's a clear increase in temperature. It's very hot. And although normal atmospheric pressure would be 1 atm, here the pressure is a little bit greater, almost twice as much. Okay, and so what we're looking at here is to try to determine the new volume of the bubble, knowing that you have pressure and you also have temperature already measured for you for those final conditions. So the initial volume would be 100 mils. The initial temperature would be 225 Celsius, but you got to convert that to Kelvin. And the initial pressure is 1 atm. The final temperature would be negative 225 Celsius plus 273, and the pressure, the final pressure would be 0.8 atm, and you're looking to find that final volume. So again, use the combined gas law, make sure you have your conversions proper, and you're going to arrive at a volume of about 112 mils. So what's kind of interesting here is that you don't get a huge difference in the volume as we did in the previous problem, but that's also because the pressure wasn't as great. And so you might say, well, the pressure was almost, twice as large. Well, that is true, but look at the temperature difference. There was almost a 200 degree, actually it was more than that. There's a 250 degree difference in temperature. And so that kind of counters that increase, if you will, of the pressure differences. So instead of it twice as much pressure, you have, to only account for, you also have here the 250 degree temperature difference. So that kind of balances out. That's why you don't really have such a large volume at the end of the day. So, these things are balancing, whether you have temperature differences, pressure differences, or, factoring in, all of this matters. All right, so then take a look at the modified example of problem 7.14. And again, I'm taking this from 279. And I adapted this. Your lung volume decreases as you swim deeper. So this goes back to almost the first problem that we did today. Okay. For every 10 meters below the water surface, the pressure exerted by the water on your body adds an additional 14.7 pounds per square inch, or PSI, to atmospheric pressure at the surface. As we know, 14.7 pounds per square inch can be converted to atmospheres, and it corresponds to 1 ATM, right? Just like how you would have the 760 millimeter mercury or the bar kind of pressure units. Here, we're just using some different units here. So then this would be the problem. What is the pressure at 10 meters? Okay, so we know that the 14.7 PSI at normal atmospheric, level, so before you even enter the water, so, on the beach, right, or on the boat before you're entering in the water, if this is going to be 14.7 PSI and the change and the pressure increases every 10 meters, that it exerts an additional 14.7, it's going to be twice that, right? And so that's the first part of the question. And so then the second one is, if a person has lung volume of 6 liters at the surface, what would be the volume at 5 meters? And then what would be the volume at 40 meters? So you can anticipate that if the volume is larger at the surface, at the water surface or boat surface, wherever the diver had originated, you can expect then with the increased pressure at depth, whatever that depth is, whether it's at 10 meters, 5 meters, 40 meters, you can expect that the volume will be decreased. And so that's what we're looking at here. So you can approach this problem several different ways. One way that I like to do it is start with your baseline, as the first increment is at 0 meters, which means at the surface. And I'm doing this with respect to understanding what the pressure increases are going to be. The second increment we're going to then take to be 10 meters. And again, why am I doing this? Because you already have atmospheric pressure even at 0 meters. So that's why we do that. It's kind of like an offset thing. Just starting with the first increment there, second increment, and then we can go on from there. So here you can have the pressure, 14.7 times 2 increments. Try to use your dimensional analysis, you get 29.4 PSI. So we know that, right? So we also would know then if we're trying to determine what the pressure is at 5 meters, then we would only take the pressure corresponding to half of that 10 meter amount, which would be half of whatever 14.7 would be, and then we would add that to the normal surface. And we would, do so corresponding to different depths. So you can use Boyle's gas law. Here we have pressure times volume, and that corresponds to a pressure and volume too. So PV, P times V is always a constant, and so the initial is going to be corresponding to the final. We're going to assume that the temperature of your body does not change. And so whenever divers do dive down, they typically wear wetsuits. And if it's really cold, then they would wear something called a dry suit. And these things will keep you relatively warm. You still feel the temperature, but your body heat is trapped reasonably well. Some of these suits are made out of a material that doesn't allow moisture really to penetrate both ways. Really, so your body heat can stay really nice and relatively constant. I say that relatively constant. Of course, it depends on the currents and things like this. And as you guys know, I also scuba dive, so I'm speaking from experience here. Usually, there's a thin layer of fluid that fills up within your wetsuit if you're diving with the wetsuit, and then it just acclimates to whatever your body temperature is. And then there's a constant kind of tug and pull of heat leaving your body, going into the water, and your body obviously continuing to try to fight that. So usually like isoprene or some other kind of material is used to try to help prevent rapid heat loss from your body. And so here we're just considering then that the diver obviously has some kind of protection in order to keep his temperature constant. So he has a wetsuit on or dry suit, whatever be the matter. So you can look at the volume, and you just using Boyle's gas law, you can say, okay, you're starting with the 14.7 PSI, and you know that that's the true case for 6 liters at the Earth's surface, right? At the water surface, I guess, or even the boat surface. But what is the volume then? Whenever you have 5 meters, well, it's 22.05 PSI, because we took half of that 14.7, and I'm not showing you that work, but you can work that out for you. half of that 14.7, which is about what, 7.35, and we're adding it then to the 14.7 increment that would be at the surface to get that 22.05 total. And so your volume is going to be about 4 mils. Actually, it should be liters. I will fix that whenever I post it. And likewise, you have going for at the 40 meters, you're going to be significantly reduced to 1 liter. Okay, so although I have 4 mils and 1 mil here, those are typos. The liters are what it's going to be. So 4 liters and then 1 liter. So there's obviously a huge drop in volume of your lungs at depth. And this is one of the reasons why you have to have a self-contained underwater breathing apparatus, i.e. scuba gear, including regulators and stuff that can help you maintain some kind of breathing capacity. And you really can't stay in the water for very long. If you were going to dive in a shallow environment, you can easily see that you have a lot more lung capacity being at 4 liters at 5 meters. So this would be relatively close. Heck, you could probably even snorkel at that point. But if you're going 40 meters below, that's obviously depths that are not amenable to snorkeling or even snoobing and things like this. I mean, I guess it could, but it starts to get really dangerous because there's not enough apparatus that you're wearing in order to maintain a certain lung capacity in order to be comfortable and to not put yourself in a dangerous situation in terms of breathing. So, that is a significant reduction in lung volume. And whenever you're diving then at depth, usually you can only stay down for maybe, between 20 and 30 minutes. Of course, it all depends on what kind of gas mixture you're breathing. Some people can use nitrox, and some people can use even other enriched gases, and that gives you a little bit longer downtimes at depth, but that's something we don't have to worry about here, obviously, but just something to be aware of. All right, so then let's consider then, so those are the examples with the gas change. So we're just going to introduce phase changes, right? Liquids, gases, solids. You guys have already known about these, you've seen about these, you know that, vaporization is liquid going to gas, melting is solid going to liquid, liquid going to solid is freezing, solid going to gas is sublimation, gas to solid is deposition, and gas to liquid is condensation. So these are just some of the terminologies that indicate that there's a phase change, okay? Now these phase changes are definitely going to be dependent upon the environment of the molecules. So is it just the one homogeneous phase, like just water? Is it a mixture of water and, for instance, isopropyl alcohol, or is it just isopropyl alcohol? So all of this matters. All of these equilibriums matter. And in this particular case, we would just be looking at just pure molecules, right? So pure systems of just, for instance, water, or just, for instance, isopropyl alcohol. So with those kinds of things, we have to look at the intermolecular forces to be able to understand where a potential boiling and or vapor pressure point might be. So on average, if we were to just do an assessment overall over just general molecules, we find that stronger attractive forces generally lower the vapor pressure and give rise to a higher boiling point. So for instance, with water, hydrogen bonding is especially prominent, and water boils at, say, 100 degrees Celsius, right? Well, if you have weaker attractive forces, then something that is going to be easier to boil off. So say, for instance, I don't know, pentane or even butane, and you even know that propane, for instance, is a gas at normal atmospheric conditions here, right? Like standard temperature and pressure, 25 degrees Celsius. So you obviously know that, with propane, you're dealing with these London forces. That's the weakest of all the forces. So the boiling point is a lot lower. In fact, it's so low that even at room temperature, it's a gas, not even a liquid anymore. You would also know that the vapor pressure at a given temperature would then be higher. So vapor pressure is another way of saying, is this going to be a stable system or is it not? Meaning, is it going to want to undergo a phase transition from, say, for instance, the liquid to a gas state, or isn't it? And so if you have a low vapor pressure, that means you have greater stability, and that gives rise to a higher boiling point. which would be in the case of water. If you're talking about a weaker system, say like butane or propane, things like that, that have only London forces as the dominant force, then that has a very high vapor pressure, meaning that it's unstable and it's going to give rise to having an overall lower boiling point. Again, higher and lower relative to what? Well, relative to other molecules, depending on their intermolecular forces, and also relative to the reference and what we're looking at. And usually that's standard temperature and pressure. So, which would be, for instance, 25 degrees Celsius, right? Or 20 degrees Celsius, I guess, in 1 atm. So again, you know that water has both polar and H bonds, and so does the isopropyl alcohol. That has polar and H bonds. It also has some non-polar character too. So just because it has 3, right, carbons involved, right? You have carbon, all those black spheres in that isopropyl alcohol indicate the presence of carbon, right? So that cartoon shows you that there's 3 carbons and 2 bonds. So water lacks that carbon, so it lacks that aliphatic character, or it lacks that carbon-carbon character, and so it's going to give rise also to non-polar bonds. So just one of those examples. All right, so your book also talks about, you know, hey, what's the difference between the spaghetti and the meatball? Really, it comes down to surface areas, right? And so the surface areas will then typically influence the boiling point and vapor pressure. So just like how spaghetti and meatballs is one way to visualize this on a macro scale, microscopically, at the intermolecular force level, this is also true, okay? And so from your book, table 7.4, here's some summary statements. For nonpolar molecules, the greater the surface area, the lower the vapor pressure and the higher the boiling or melting point. We just discussed that in the previous slide, using, for instance, like butane or propane as an example, something that only has like London forces having the most dominant kind of intermolecular force, then it's going to give rise to a little bit of instability, and then help that transition from, for instance, the liquid stage to the gas stage. So here you have similar sized molecules, different attractive forces. The stronger the attractive forces, the lower the vapor pressure and the higher the boiling point, right? So there's also that category, and then you have molecules with the same attractive forces. So the stronger and more numerous the attractive forces, the lower the vapor pressure and the higher the boiling point. So these are all part of what we're trying to explore here as we're trying to compare molecules of different, you know, not only character, but having different vapor pressures, boiling points, and like trends. So let's take a closer look, because sometimes the tables aren't exactly helpful. I did highlight that from the book, but that sometimes isn't as helpful as looking at some hardcore examples. So here you go. So here's some straight chain alkanes. These are also called aliphatic molecules. I think I dropped that term in there before. And you can see that there is no conjugation here. So there's no double bonds. We're not trying to complicate the picture. These aren't functionalized in any other way with like hydroxyl groups or anything like that. There's no carbonyls present. These are just carbon-carbon chains. What happens to the boiling point as the carbon-carbon chain length increases? Well, as you go from methane to decane, you can see that the boiling point increases significantly. And you guys know that whenever you put gasoline in the tank of your vehicle, right, you're going to have a lot more larger than carbon-carbon molecules. For instance, octane, right, that has a boiling point of 125 Celsius. So you don't have to worry about the liquid quickly evaporating to the atmosphere as you're putting that into your vehicle. So for the same type of attraction, the molecular size impacts relative phase stability. What we mean by that is all of these have London forces as the dominant intermolecular force. So that's what we mean here by for same type of attraction. So then I underline molecular size, meaning that the number of carbons. If you go from 1 to 10 carbons, there's an increase in boiling point. So I think that that's hopefully pretty clear. Now, for the same molecular formula, the structure impacts the phase stability. So this is pretty interesting, right? So if you have 2 molecules, and here I show you hexane. So you have the straight chain on the left, and then you have the branched 2,3-dimethylbutane. Also has 6 carbons, but they're arranged differently, right? So these are isomers of one another, as you guys are already very much familiar with. And if you were to look at the cartoons there, with these ball and stick models, for instance, it becomes pretty clear. I mean, even the skeletal model even shows you this, but the temperature is definitely different, right? 69 degrees is the boiling point for hexane, whereas it's 58 degrees for the alternate structure and for the 2,3-dimethyl butane. So really interesting here. So the longer, straighter chain give rise to a higher boiling point. The dimethyl butane structure is generally a little bit more, I don't know, spherical in nature. And so by virtue of that surface area, it helps to depress the boiling point just a bit. So kind of interesting. And as you know, those are structural isomers. Okay, so let's compare then several different molecules. I call it the molecular thunderdome, and this is round one we're going to do. So obviously we're going to do more rounds. Which has the higher boiling point or lower vapor pressure between these two molecular structures here. So you have obviously a couple different formats of this. In fact, the one on the right has the double bond, whereas the one on the left doesn't, right? So you have 1, 2, 3, 4, 5, 6, 7, 8 on the left. So you have 8 carbons on the left, and you have 1, 2, 3, 4, 5, 6, 7, 8. You have also 8 carbons on the right. Okay, so each of these has 8 carbons. How do we approach this? Well, look, we know that the London forces are going to be the strongest attraction of both. Okay, so even the presence of a double bond or even triple bond isn't going to change that. You don't have significant polarity that is arising from either of these molecules. And because of that, that is why the London forces are dominating. But we know that the molecular formulas are different. For instance, the hexane has more atoms. How does it have more atoms? Well, it has 2 more hydrogen atoms because it lacks that double bond there than that molecule on the right. Okay, and so what that means is that in this particular case, the more atoms means greater stability and higher boiling point. Okay, so you can see that the structure on the right, it kind of dips down. It almost looks like it's been funneled a little bit, right? Almost like a cup kind of structure. Again, we have already recognized that surface area makes a big difference in terms of giving rise to whatever the boiling point will be. Even further, that cup-like kind of opening as it opens up, that is also because there is the presence of a double bond, that lets you know that this is a cis configuration, right? So any double bond kind of molecule will have the opportunity to either have cis or trans in the environment. If this was trans, then you can take the 1, 2, 3, 4 carbons that are on the right side of that structure on this molecule on the right, and you would just rotate that down 180 degrees, right? So it would be angled instead of going, you know, northeast, if you will, if the direction of the screen is going to be north, and to the right it's going to be east, and to the left it's going to be west, and obviously down will be south. So it's going to go from northeast to what? Southeast, if we were to rotate that, and it would become a trans. So here in the cis configuration, this is less stable, it's going to be more reactive, and this system will also then give rise to differences in boiling point. So C8H18 versus C8H16, you know then that the higher boiling point will basically be the octane, right? And so, just like on the previous example where we had the difference there with like more spherical looking shape with the hexane difference, right? It was the one, the figure on the right, without me having to go back, I believe it was the dimethyl butane. That is the one that had the lower boiling point. So in this particular case, this octene molecule here in the cis configuration will also have, the lower boiling point. So what about these isomers? They are unrelated. And how do we know that? Because they're different number of atoms, right? It's the double bond eliminated that kind of approach. So although they both have 8 carbons, because they lack overall the difference in hydrogen atoms, these are not isomers, they are unrelated. All right, molecular thunderdome, round 2. which has a higher boiling point, or if you prefer, a lower vapor pressure. Ooh, so you have dimethylamine versus ethyl alcohol, or you can even just call that ethanol perhaps. All right. So we have to look at these. So now both of these have nitrogen and oxygen. Not both, but the one on the left has nitrogen, the one on the right has oxygen. That's a requirement for H bonding. So we already list this as saying, hey, look, H bonding is strongest attraction in both. There is the opportunity for those bonds to form. So London forces, although they do have that as one of the intermolecular forces, that isn't the most dominant. They are polar, and in fact, they both have H bonds. There are no ions present, so it can't have ions or any kind of ionic bridges or any kind of ion-based attractions there. And these are definitely not going to be the dipole-dipole, because that would be the second weakest, right? Or the next to last weakest bond. And it's the reason why that's not going to be the winner, is because with hydrogen bonding, the presence of the nitrogen or oxygen, or for that third element, fluorine, which it can also perhaps have, is a requirement for the H bonding to be present. So here in this particular example, you have, and it should be dimethylamine. Dimethylamine has one H bond acceptor. It's the N. And in the ethanol, there's two H bond acceptors, okay? Because there's two lone pairs. Again, this is what we're talking about. How many lone pairs? And if you don't recognize that right away, then it probably helps to draw the Lewis structures and go and revisit that. But there's only one lone pair of electrons that reside on nitrogen. And there's two lone pair of electrons that are residing on the oxygen in that ethanol molecule, okay? So that is why we have one versus two, okay? And the more H bond character means greater stability and higher boiling point. So how do we know what is going on? These are both unrelated, but because there's two H bond acceptors with the oxygen, that means that there's more likely to have greater H bond character with respect to greater stability, i.e. higher boiling point and lower vapor pressure. That will then necessarily be the ethanol molecule, okay? So because two is greater than one, right? And we're talking about lone pairs. The lone pairs on oxygen versus the lone pair on nitrogen, okay? Now, are these related? Heck no. These are completely different molecules. And so that's why I just listed there that these are not isomers, they are unrelated. All right, molecular thunderdome, round 3. Here, what we can do, and this is based off problem 728, we can rank in order of lowest to highest boiling point, or higher to lower vapor pressure. All right, so we're starting with 3 different molecules. Now, right off the bat, you can see that we have what looks to be a type of ether here on the left. You have an alcohol in the middle, and then you have just the straight chain aliphatic 1, 2, 3, 4 carbon molecule on the right, okay? So as we know that there is, that all of these, I mean, you have 1, 2, 3, 4 carbons in that ether. You have 1, 2, 3, 4 carbons in the alcohol, and then you have 1, 2, 3, 4 carbons in that just straight chain carbon molecule on the right. So what you have here is the same number of carbon atoms, but you just have some different substituents. So ethanol has the OH group present, and then obviously the ether has the oxygen that splits the two ethyl groups, right? So diethyl ether, I guess you can call that. But here's the difference that you're trying to look at. What is going to have lowest to highest boiling point is going to be based on the intermolecular forces. And so it helps to write out all of this in the molecular forms, maybe that you might be more familiar with, but you know that the one on the right, this butane molecule, it's only going to have London forces as the most dominant. We know that the alcohol is going to have not only London forces being present, but not dominant. It'll also have some polarity, and it has likely the hydrogen bonding by virtue of the 2 lone pairs that naturally reside on the oxygen. Okay. Now, interestingly, on the left, you also have for instance, some London forces present, just as the other ones did, but it's not dominant. And it's probably going to be polar as well. But here's going to be the key. Although it also has the 2 lone pairs of electrons, there's not a whole lot of extra hydrogen atoms that are present that are going to be able to bond with that. So this gives rise to an interesting scenario. So although both have oxygen, basically it's ether and the alcohol, and they both have the same number of lone pair electrons, do they have sufficient hydrogen atoms available in order to bond with them? And that's not going to be the case. So you have here, we've already stated it, London forces are good for the butane. Hydrogen bonding is the strongest attraction for butanol. It's going to be the dipole-dipole, okay, for the diethyl ether, all right? And so here you have, by the strength of force, you know that the dipole-dipole is next to weakest, or it's just another way of saying that, just a little bit stronger than the London force, than the London, or dispersion or van der Waals type of intermolecular forces, right? So you can just arrange them that way. So the ether definitely has stronger bonding than the, or intermolecular forcing between the molecules relative to butane, and then of course butanol is there too. So again, I think that that's really important. So the hydrogens from the ether, they're not able to hydrogen bond with the lone pairs of oxygen, okay? So if you have a solution where you have then more than one molecule of this diethyl ether, don't expect that the aliphatic hydrogens, okay, the ones that are attached to the carbon, so the CH3 or the CH2, are going to be able to participate in hydrogen bonding. I think that that's a really important distinction to be made here. Whereas you have the hydrogen group that's already attached to the oxygen for the butanol case, right? That alcohol that for the middle structure. That's really important because you know that, for instance, let's just think about water, H2O. You have oxygen, it has the 2 lone pairs, and you have 2 hydrogens on either side. And we know that hydrogen bonding is the dominant intermolecular force for water. So that automatically tells you that if you have an OH group present, you must then consider hydrogen bonding to be probably the dominant structure, of course, unless there's ions present. But then you also need the oxygen and hydrogen, right? Both together, present together, to be considered for hydrogen bonding as the dominant intermolecular force. If you don't, as in the case of this diethyl ether, then you cannot have the hydrogen bonding. I mean, there might be some weak, but it'd be really weak interactions between the hydrogens that are attached to the second, or the first carbon there, but it's just not going to be, that case. So here I had highlighted butane is less than diethyl ether is less than butanol. If you wanted to do that with respect to the actual intermolecular forces, which I would always recommend, for instance, if you're going to have, if you're going to just examine anything, whether this is on a quiz exam, in the Master in Chemistry homework or whatever, go ahead and just slow down and write everything that you do know, like London is less than dipole is less than H bond. So that's another way to look at this problem. So I want to do a further example because this is important. So from the Master in Chemistry, you can rank the 4 molecules from highest to lowest boiling points. And this is from the assigned Chapter 7 Master in Chemistry homework. I don't remember which problem it was on purpose because I want you to be able to look at that. But here would be a great example. So you have now four different molecules. You have a methyl acetate, you have aminobutane, you have pentane, you have aminopropanone. The first thing you need to do is understand what type of molecules these are. So you will know that the lowest boiling point will have the weakest intermolecular bonding. We already know this. Remember, propane is a gas at room temperature. It's very stable and relative to the normal standard temperature and pressure. And so it's just natural for the molecules to want to go from liquid phase to gas phase, right? So I'm using that as an example saying, hey, look, lowest boiling point is the weakest intermolecular bonding. So you have the choice between this methyl acetate, which you must recognize as an ester. It has the OO character, kind of looks like the carboxylic acid, kind of structure almost, right, where you have the COOH, but instead of the H, you have the R. So there's obviously a methyl group on either side of that molecule, and that's why it's an ester, okay, and not a carboxylic acid, for instance. Here you have aminobutane, right? It's a primary amine because the nitrogen is attached to the one carbon, but it has a significant amount of aliphatic or straight chain alkane-like character. You also have pentane, which is just an alkane, and then you also have aminopropanone, okay? So here you have an interesting situation. We haven't really talked about it a whole lot. We will whenever we start talking more about amino acids and stuff. But you have an environment that includes a carbonyl next to an amine. And whenever you have that carbonyl next to an amine, the new term for that in the description would be an amide. So you have an ester, you have a primary amine, you have an alkane, and you have an amide. And you're asked to figure out which one of these has the highest and which one has the lowest, and then you got to get the ones in between. So how I would approach this is just, besides identifying what type of molecule they are actually working with, which I think is really important, because once you do that, that can help you better understand about some of these differences in all these intermolecular forces. In other words, what is available to me in terms of trying to understand which intermolecular forces might be dominant. So first of all, we can look at which ones are polar. We already know that pentane is not, okay? So just to be pedantic about this, let's list the ones that are not. So you have the ester, you have the primary amine, and then you have the amide. All of those are polar, okay? So they're pretty much equal right now. So we know that the one that has the weakest intermolecular bonding is going to be pentane, and that's going to be obviously then on the far right. If we were to rank these from left to right, going from highest to lowest, pentane is going to be on the far right. So really the discussion comes then amongst these three polar molecules. So we then have to ask, just like how we had the strength of the intermolecular forces from yesterday's session, or the part 1 session where we had London forces, dipole-dipole, hydrogen bonding, and then ion-dipole versus ionic, right? Those are the 5 dominant intermolecular forces that we discussed. So here you have H bonding being possible among the 3. Is it even a possibility? Well, methyl acetate will rank next to last because it lacks the hydrogen that would be, I'm going to call it the attendant hydrogen, that would have been required for hydrogen bonding to occur. Just like in water, how you have the OH groups, right? You have 2 of them because it's H2O. In this ester, there are no examples of the OH group here. And so that's why the ester will not have the hydrogen bonding being possible. Now, alternately, instead of having the OH, remember the other ones that are possible for this include the N, the nitrogen H, and then also fluorine is also a possibility too. So the one that has the nitrogen with the lone pair that has a hydrogen, I'm going to call it an attendant hydrogen right next to it, that one could be eligible then for hydrogen bonding, right? And then you also have it with respect to the aminopropanone, the amide group, right? Because that also has an amine group present. So both of those have the hydrogen bonding possible amongst all those 4 molecules. So you already know that pentane is the last. Now you know that the methyl acetate, which is an ester, is next to last. So then you just got to try to figure out which one is more polar. Well, the amide is going to be more polar by virtue of that carbonyl. So you know that electron density is going to be pulled by that oxygen relative to the carbon that it's directly bonded to, as well as weakly, though, albeit weakly, the carbon and electron density from that's on the left-hand side of that molecule, right? That ethyl group, basically. So you have one being more polar than the other. You already know that the straight chain amide group there, the primary amine, the aminobutane, is not going to have a lot of additional polarity pull, only relative to whatever that amine group is, okay? But the amide already has that, plus it has the presence of the oxygen within the carbonyl. So you know that's going to be the most polar. So going from highest to lowest then, you would have the amide is greater than the primary amine, is greater than the ester, is greater than the alkane. And I wrote it like this because I think it's important so that you know, as you're approaching these problems and for your studying purposes, about the potential of some of these functional groups and having their natural, I guess, bearing on boiling points, vapor pressures, i.e. phase stability. So this is what we're showing here. So the amide is the aminopropanone, the primary amine is the aminobutane, the ester is the methyl acetate, and the alkane is the pentane. So that's where we're at in that case. Now, since we had just talked about ice a little bit, I just wanted to just throw this out there. There are a lot of different ice cubes that you can make. And I say ice cubes, you know, and I'm kind of chuckling about it here, but there are a tremendous amount of different structures that you can get if you adjust the temperature and if you adjust the pressure. So there's not just like the one type of ice that's made in your kitchen freezer or the bags of ice, which all this stuff looks a little different, and it is somewhat different depending on the conditions used to make the ice. And so I mean, I even think that there's a band called Ice 9 Kills, and also in Kurt Vonnegut's Cat Cradle, he talked about a very dangerous form of ice, and I believe that was also Ice 9. You know, we don't have access to that very, you know, very easily, so it's not like you have to worry about, geez, what type of ice am I having in my drink today or anything. I mean, you know, you look at the pressure here, you're talking about gigapascals, and you're talking about huge temperature variations in order to be able to get this certain types of ice structures. Normal atmospheric Pascal would be around, I don't know, 101,000. So if you're going from 101,000 to gigapascals, there's going to be a significant amount of pressure required to be able to get ice to be in that kind of shape. So here we're not around that. We're just we're down here where you have like the octahedral, or I mean the hexagonal ice, right? IH. So that could be right in this area here, and that would be the more dominant form. But just kind of interesting to allude to you guys. Just wanted to share it with you since we are doing some phase transitions. And this is the case, you could make the argument for many other types of solvents or materials. But even to this date, you know, there are now 17 different forms of ice. So, but again, the only one that you have to worry about is the hexagonal form, because you can, you know, just, I mean, that's just the safest, right? Most normal. So just kind of fun. All right, so we're going to be talking about solubility in a pretty regular manner here. But if we consider then attractive forces and solubilities, just because we've been talking about the different types of intermolecular forces, I think it's important that we start off with the golden rule of like dissolves like. So polar dissolves polar, right? So is it going to be possible for oil and water to mix? Probably not, right? Even though there is a certain small range where oils and waters can mix, by and large, they cannot mix. You have what's called phase separation. So you also have nonpolar dissolved nonpolar, right? So all of this is probably then very helpful to understand. So if you had, for instance, some kind of sticky substance that, like an ester, right? So if you had an ester from a slime that you made, or another type of ester, I don't know, that was created. Remember how we did a condensation reaction with the erythritol, and we added that to citric acid, right? We created an ester. It could be very sticky. So one way of removing that then would be taking a similar weakly interacting solvent. It could be made up of an ester. It could be something like, oh, I don't know, maybe some kind of dissolved form of methyl acetate, and you can use that to like remove it. Or you could use just some straight chain carbons. Maybe you can use a little bit of pentane, or maybe some hexane, maybe even some benzene to try to help remove that, right? That would be an example of a nonpolar dissolving really a nonpolar. Although not, you know, not completely, because we know that the esters do have the dipole-dipole interactions, but again, those intermolecular forces are next weakest relative to London forces. So sometimes you can get some of these intermolecular forces that are close in character to be able to be work together, right? So that's just the example there. So if you were to look at oil and water, you know that oil and water do not dissolve. In fact, there's here's an image of some water, and the oil is the yellow. You can see that, nice spheres of this forms. Does, for instance, though, sucrose dissolve in water? We know that sucrose is polar, right? And it has a tremendous amount of hydrogens present, a lot of OH bond character. You can see that, within the alcohol groups that it has, and then it has obviously a ton of OH groups too. Well, water also has OH groups. So if sugar is dissolving in water, which it does, obviously there's limits to all these things, so you can't put in, sugar unlimited into a certain amount of volume of water, because it'll ultimately become what we call saturated. But if you had like a teaspoon of sugar dissolved in, like, I don't know, 10, 15 mils of water, we'll get the dissolution, and the dissolution would occur via the hydrogen bonds. So I think that is pretty important to say. So again, let's look at golden rule, like dissolves like, and you have a bunch of different medically important compounds here. You have penselenium, this is an antihypertensive. You have methamphetamine, this is recreational, right? But this is also sometimes prescribed for ADHD. And you have Remeron, which is an antidepressant. What you would have to look here is that you would have to understand first, if it's going to dissolve in something, and this helps you better understand what are the conditions in which you should take the medicine. For instance, if you're going to take something that is going to be very polar, then you could probably just use water to take that. If you're going to use something that has kind of a combined character of polar and non-polar, you might want to eat something with that, or at least consume something that has some fatty character or oily like character, right? Because that will help the dissolution of that compound in your body, and hopefully then, as it passes through your GI system, uptake into your system. So the penselenium, we have this example here. This is decidedly polar, and I know that there's this aliphatic straight chain carbon in between here, but you know what? You also have two ionic charges here, both with respect to that nitrogen. So you have these ordinary, ammonium, species here. You have two of them. That's pretty pronounced. So although that the aliphatic character is present, that is not going to be the dominant character, and in fact, it's actually at the other end of the spectrum, having ions present. The ion dipole interactions are very strong relative to any kind of London dispersive forces that there are. And so taking this with water would probably just be fine, because the water molecule, while that can also participate in hydrogen bonding, okay, the ion dipole interactions would be very strong with respect to this molecule whenever it's taken with water. If you're going to take a look at methamphetamine, although that you do have hydrogen bonding that can take place, right? You see the nitrogen there. It is a second degree, right? Nitrogen, but the problem is it's so overwhelmed by the fact of this aliphatic chain immediately, to the left of that nitrogen, followed by that aromatic ring, which is non-polar as well, that overall the hydrogen bonding is not going to be enough to, especially because there would be perhaps one lone pair of electrons, right? This isn't like it's oxygen that has two lone pair. And so it's just not enough to try to make this an overall polar molecule. So it's largely non-polar. So, to be able to take this kind of medicine, you would probably say it might be wise to eat this with food, and some food that maybe has a little bit of fat to it in order to help dissolution. And this other one, the Remeron, boy, we have a lot of nitrogen in there, but the nitrogens are pretty much all saturated, right? We don't have a lot of hydrogens that are attached to these and such. And so just by virtue of that alone, and with the huge amount of aromatic character and then aliphatic character, actually it's all wrapped in rings and stuff, that this is also going to be non-polar. So this would be another type of medicine that you would probably want to take with not just water, but something that has a little bit of fatty character, I'm not saying that, you can drink oil like, I don't know, like canola oil or any kind of like dressing oil, but you would want to have something that actually has a bit of fat in your food whenever you're going to take this, okay? If you just have glucose, right, this would be the blood sugar, right, or dextrose, as it's also known. You know that that's polar by virtue of all of the different groups that it has, especially hydrogen bonded groups. I mean, look how many. It has 1, 2, 3, 4. It has 5 OH groups already present, and that's pretty significant because in this ring structure, you have 6 carbons. So out of those 6 carbons, you have 5 hydroxyl groups that are rising to the hydrogen bonded structure. So that's pretty important. So glucose is pretty polar. Well, guess what? We already know our bodies are made, and well, in terms of our blood, it's highly compositioned of water, right? Composed of water, and water is polar, so it makes sense that blood glucose would be in our blood. It's pretty straightforward. Naproxen, okay, so an ingredient in a leaf. You do have some character here. So this is not an ester, this is a carboxylic acid. There is some OH groups here. You have a tremendous amount of non-polar character though. Holy cow, right? Looking at all of this aromatic character from the middle of the molecule to the left-hand side, and then it ends, right, with an ether. So looking at that and recognizing that there is a polar head group then on the right-hand side, but by considering that there's only 4 and really only 2 atoms that are going to give rise to the hydrogen bonding and polarity. I mean, even if you said there was 4 atoms total, look at the 4 atoms here on the right-hand side of naproxen relative to everything else that is present in that molecule. It's completely overwhelmed. If this happened to be charged, then you might have that being more of a tendency to probably being polar. But because in this format, you don't have charge like you do in the upper left here for the pentylenium anti-hypertensive polar molecule, then you would say that the non-polar character of this molecule, this naproxen, is going to overwhelm the polar character that exists with that carboxylic acid type of functionality there on the on the right hand side. If we were to look at vitamin K, here's another great example of this, right? You have this huge aliphatic chain, right? That's decidedly non-polar. And then you also have all these carbonyls and stuff. And the carbonyls, although they have lone pairs of electrons, there's not a hydrogen directly attached to it. And so H bonding isn't going to be one of the primary intermolecular forces. So this is also very important to know, right? So this overall is going to have a non-polar character. What about vitamin B6? All of a sudden, it's a little bit different. You have 1, 2, 3 OH groups in this molecule. And those OH groups, they have their lone pairs of electrons on each of the oxygens. Plus, you have nitrogen here too. Now, nitrogen isn't attached to any of the hydrogen, so really that's going to not really play into the role here. But because it is, consisting of 3 hydroxyl groups, which can give rise to hydrogen bonding, you could probably take the vitamin B6 with water. Vitamin E, very similar thing, although there is an OH group, kind of like how we talked about the naproxen, it's there. We know that hydrogen bonding can take place, but look at the size of the aliphatic carbon, as well as the other non-polar regions. You have the cyclic ether immediately to the left of that aliphatic chain, and then you also have that aromatic ring, which is also non-polar. That's going to be an overall non-polar. That OH group isn't going to be able to do enough to try to make that an overall polar structure. And then vitamin C. You know probably that you can take vitamin C, like the packets that you can just dump into a drink. Well, guess what? You have 1, 2, 3, 4 hydroxyl groups attached in this molecule. So you know that this is going to be obviously already polar anyway. I mean, you have the carbonyl, but those oxygens again, and this is like an ester kind of environment. The ester is not very strong relative to the hydroxyl groups and the hydrogen bonding that's present. So you know that the hydrogen bonding with 1, 2, 3, 4, that will likely overwhelm that ester, and that will give rise to a more polar molecule. So you could just add water, like if you had the powdered like vitamin C or like the emergency type of mixtures, you can just add that to your water bottle, or a glass of water, mix it up and drink it. Vitamin C is also added to different beverages, right? Sometimes it's added to orange juice, for instance, sometimes, or milk. Actually, vitamin D is the one that's added with milk, and vitamin D actually it's done that because it needs some fats in order for that to be absorbed better. I jumped the gun there a little bit, but just wanted to state that. So if you see some drinks that have added vitamin C because they want to try to improve the overall vitamin C uptake that somebody will have, then it's going to be because it is polar. It can readily be added into a water-based beverage, and you can just take it as is without having to worry about your stomach getting upset. So I had just jumped the gun previously talking about vitamin D. This is vitamin D3, cholecalciferol. This is sometimes added into milk to try to get that vitamin D calcium uptake right at the same time. Well, guess what? Is this polar or non-polar? You can tell by virtue of the tremendous amount of non-polar character relative to the one OH group here that would give rise to a polar character, that this would be overall non-polar. And so that's why we have that situation. So again, I've discussed the water soluble versus fat soluble impact that each one of these can have. And I think that that's going to be a great place to stop right now. So we will then begin next with oils and esterification.